Welcome back, everyone. I'm so pumped for this deep dive. We're going to be talking about computer programs. The things that make our computers and smartphones do all the amazing things they do.
It really is mind-blowing when you think about it. It's like magic, how these lines of code can create entire digital
I
worlds.
know, right? It's like a secret language that controls everything.
Right.
So our mission today is to explore how those instructions are written in a language that even a CPU can understand.
Exactly, because at the most fundamental level, computers operate on binary code.
Okay, binary code, ones and zeros. I get the concept, but to be honest, it always seemed a bit like a secret code to me.
Well, it would be incredibly difficult for humans to write entire programs directly in binary. That's why we have assembly languages.
So it's like a translator, right?
Yeah,
Helping us speak the computer's language.
precisely. Assembly languages use what we call mnemonics, which are short, memorable commands that represent complex binary instructions.
Mnemonics. That sounds interesting. Can you give me an example?
Sure. Imagine a mnemonic like LDA, which tells the CPU to load accumulator. Basically, it's grabbing data from memory and putting it in a temporary spot where the CPU can work with it.
Okay, so LDA. So are there a bunch more of these mnemonics?
There are quite a few, but they're designed to be pretty intuitive. You have commands like ADD to add values and STA to store values back into memory. It's all about building a sequence of commands.
Right, building a sequence of commands using these simple, easy to remember words. But wouldn't it still take forever to write complex programs like that?
You're right. As programs get more complex, writing them purely in assembly language would be really, really time consuming. That's where high-level languages come in.
High-level languages, I've heard of those, like Python or C++. So how are they different?
High-level languages are designed to be much more human-friendly. They abstract away a lot of the low-level details of assembly languages.
So is it kind of like the difference between giving someone step-by-step directions and just giving them an address and letting them use a GPS?
That's a great analogy. And that shift to high-level languages really opened up programming to a much wider audience. It's a big reason why we have so many incredible programs and apps today.
Wow, that's amazing. It's like it democratized the world of coding. But okay, I'm a little fuzzy on something. I've seen the terms source code and object code
Uh-huh.
before, but I'm not entirely sure what they mean.
Well, think of source code as the raw, human-readable code that a programmer writes. It could be an assembly language or a high-level language.
Okay, an object code.
Object code is the machine executable version of the source code. It's the result of a process called compiling or assembling.
Okay, so source code is like a recipe. Object code is the actual cooked dish.
Exactly. The CPU can't execute the recipe. It needs the cooked dish, the object code. That's how the program actually runs.
This is all making so much more sense now. But programs can't just be a list of instructions, right? They need to make decisions.
Absolutely. That's where conditions and jumps come into play.
Conditions and jumps, what are those?
It's how programs make choices based on certain conditions. Like, imagine a traffic light. It needs to change based on whether there are cars waiting.
Right, so it checks if a car is there
Yeah.
and then changes the light accordingly. I see,
Yeah.
I see. But you know what always gets me? Loops. I never really understood those.
Loops are essentially a way for a program to repeat instructions multiple times. Like if you wanted to calculate the sum of all the numbers from 1 to 100, you could use a loop to repeat the addition process 100 times.
It's like automating those repetitive tasks.
Okay, that makes sense. But what's really amazing to me is something like facial recognition software. It's incredible how a program can analyze a human face and identify a person.
It's definitely a powerful application of programming.
Yeah.
You're right, it seems complex, but at the end of the day, a computer is basically a number cruncher.
Yeah, so a human face gets turned into a bunch of numbers that the program can understand and work with.
Okay.
Okay, that makes sense. But I'm curious, where are these programs actually stored? Well, it depends. For smaller devices, programs are often stored permanently in ROM, which stands for read-only memory.
ROM, so it's like permanently etched into the device.
Exactly. But for larger systems like PCs, programs are typically stored on a hard drive or SSD and then loaded into RAM, which is random access memory, when you want to run them.
Right, RAM is more like a temporary workspace. So what happens when you first turn on a device or hit the reset button? What tells the CPU where to start?
That's the job of the reset vector. It's a memory address that points to the location of the first instruction of the program.
Oh, so it's like a starting line for the program.
Yes. And that process is remarkably consistent across all sorts of computers, from tiny microcontrollers to huge supercomputers.
This is fascinating. We've covered so much ground already, from those mnemonics to program logic. I'm ready to dive even deeper.
It's pretty amazing how all these concepts come together to create the programs we use every day.
Yeah, I know, right? But I have a question. We've talked about individual instructions, but how are those instructions actually organized within a program?
Oh, well, that's where program structure comes in. Just like a good book is divided into chapters and sections, a well-written program has a clear structure too.
So you're not just writing one massive chunk of code.
Exactly. We break programs down into smaller, more manageable chunks called functions or procedures.
Functions. So it's like dividing a complex problem into smaller, easier to solve pieces.
Precisely. And breaking code into functions also makes it much more reusable. Let's say you've written a function to sort a list of names alphabetically.
Right.
You can reuse that same function in other parts of your program or even in completely different programs.
That makes a lot of sense. So it's kind of like having a toolbox, right?
Yeah, a toolbox full of pre-built tools that you can use whenever you need them.
I like that analogy.
Mhm.
But how do these functions actually work together? I mean, do they just operate independently?
Not quite. They can interact with each other by passing data back and forth. It's like a relay race.
Okay, so one function might perform a calculation and then pass the result to another function.
Exactly. And this passing of data is carefully managed through things called parameters and arguments.
Parameters and arguments. Okay, I'm not familiar with those.
Think about ordering a pizza online. You choose your crust, toppings, and size, right?
Right.
Those are your arguments. The website takes those choices and sends them to the pizza restaurant's system as parameters instructions on how to make your pizza.
Oh, so the parameters are like the blueprint for the pizza and the arguments are the specific ingredients.
Exactly. It's the same in programming. A function has parameters that define what kind of data it needs. And when you call that function, you provide the actual data as arguments.
Got it. That makes sense. So once a function gets its arguments, it can do its thing, its task, and then return a result, like a delicious pizza.
Perfect analogy.
This whole system of functions is fascinating. But how does a program know which function to execute first? I mean, is there some kind of master plan or something?
That's where program logic comes in. Program logic is the sequence of steps that a program follows to achieve a goal.
So it's not just a random jumble of functions. There's an order to how they're executed.
Absolutely. And just like a roadmap can have different routes and detours, program logic can involve different paths and decisions.
Right, like those conditions and jumps we talked about earlier. That's how programs make decisions, right?
Exactly. And another important concept is branching.
Branching, what's that?
Branching allows a program to deviate from its normal sequence of instructions and jump to a different section of code based on certain conditions. It's like taking a detour on your roadmap.
I see. So branching is about making those dynamic decisions. But what about repeating actions? Like with those loops we talked about.
Right. Loops are super important for automating repetitive tasks. Imagine writing a program to process 1,000 customer orders.
Yeah.
Instead of writing the same code for each order, you could use a loop to iterate through each order and perform the necessary actions.
Wow, that's a huge time saver.
Loops are all about efficiency. And there are different types of loops for different situations.
Different types. Like what?
Well, you have things like for loops and while loops, each with its own specific purpose.
So it's about choosing the right tool for the job, the
Yeah.
right loop for the right situation.
Exactly. But with all this branching and looping and decision-making, it does get complex. So how do programmers keep track of it all?
That's a good question. I was just thinking that.
Fortunately, there are tools to help manage all this complexity. One of the classics is flowcharts.
Flowcharts. Those diagrams with boxes and arrows.
Yep. They use different shapes to represent different actions in the program. It's like a visual blueprint of the program's logic.
Okay, so a visual aid to help understand the flow of the program.
Exactly. And another popular technique is pseudocode.
Pseudocode. What's that?
It's like writing a rough draft of the program using plain English-like statements without worrying about the strict rules of a programming language.
So it's a way to plan out the logic before writing the actual code.
Exactly. Pseudocode is a great way to brainstorm and get the big picture right.
This is all really interesting. We've gone from those individual instructions to functions to program logic. It's amazing how it all comes together. But I'm curious how programs actually interact with the outside world, with us.
Well, that brings us to input-output operations, or I/O for short.
Input-output.io. So it's how a program communicates with the world outside of itself.
Precisely. Think about when you type on your keyboard. The program receives those keystrokes as input, processes them, and then displays the text you typed on your screen as output.
Oh, I see. So that's I/O.
Exactly. And it's happening constantly all around us and at incredible speeds.
Wow. I never really thought about it like that before. But it's not just keyboards and screens, right?
Right. Programs can interact with all sorts of devices and systems through I/O. Like, think about databases.
Databases.
Yeah, programs can read data from and write data to databases using I/O. Like when you do a Google search, the search engine is using I/O to access massive databases of web pages.
Oh, wow. So every Google search is a program interacting with a database behind the scenes.
It is. And the same goes for the internet itself. Programs use I/O to send and receive data over networks.
That's how we browse websites and send emails.
Exactly. I/O is what connects programs to the outside world, making them incredibly powerful tools.
Mind-blowing. I/O's happening all the time, all around us. It's the bridge between our digital world and the real world.
You got it.
Wow, I/O's everywhere. It really highlights how connected our digital world is to the physical world.
Yeah, it's pretty amazing, and we've only just scratched the surface of what programs can do.
I know. It's mind-blowing to think about how all these concepts we've been talking about come together to create the technology we use every single day.
It really shows the power of programming, doesn't it? And the incredible creativity of the people who design and build these systems.
You know, it's easy to take all this complexity for granted when we're just using our devices, but it's important to remember the ingenuity and hard work that goes into making it all possible.
Absolutely. And what's even more exciting is that this digital revolution is still in its early stages. There's so much more to come.
Oh, I completely agree. Speaking of exciting developments, one area I find particularly fascinating is artificial intelligence, or AI.
AI is a game changer for sure.
It seems like every day there's a new breakthrough. AI is being used to diagnose diseases, drive cars, compose music, even create art. It's like science fiction is becoming reality.
It really is remarkable, and a lot of these advancements are driven by machine learning.
Machine learning. Can you explain that a little?
Sure. In traditional programming, we give the computer very specific instructions on what to do.
Right.
But with machine learning, we create algorithms that can learn from data.
So instead of programming every rule and instruction, we give the program a ton of data and let it figure things out on its own.
That's the basic idea. Of course, there's a lot more to it than that, but the key is that the program can adapt and learn, rather than just following a fixed set of instructions.
Wow. So the program's actually learning and improving over time.
Exactly. And that's what makes AI so powerful. It has the potential to revolutionize so many aspects of our lives.
I can definitely see that.
Yeah.
But to be honest, it's also a little intimidating. I mean, are we heading towards a future where machines are making all the decisions?
That's a question that's been debated for a long time. And there's no easy answer.
Yeah.
But I believe that even with all the advancements in AI, we'll always need human creativity and ethical guidance to shape how we use these powerful tools.
That's a good point. Ultimately, programs are tools, and it's up to us to use them responsibly and ethically to create a better world.
Absolutely. We have a responsibility to ensure that AI is used for good, for the benefit of humanity.
Well said. This deep dive has been amazing. I feel like I've learned so much about the world of programs, from the basics of instructions to the potential of AI. It's incredible to think that it all comes down to lines of code.
It is pretty amazing, isn't it?
It makes you appreciate the power of human ingenuity, how we can create these complex systems that are changing the world.
It's definitely something to think about. And who knows what incredible innovations are just around the corner.
Exactly. The future of programming is wide open. So to everyone listening, thank you for joining us on this incredible journey. We hope you've enjoyed exploring the fascinating world of computer programs.
And remember, the power to shape the digital world is in your hands.
Until next time, keep exploring, keep learning, and keep imagining the possibilities.